So, I make an effort to try to explain, when we're doing trig substitution or whatever, where that kind of thing might come from. But it's clearly true that calculus 2 can sometimes seem disconnected from applications, let's say. So it's good that we have a few days because, calculus 2 has major applications, and one of the major applications is probability. And you'll be taking if you haven't already, a dedicated probability course with Mr. Saloon, so we're not going into details here. But we'll talk about probability, and we'll talk about the integral, and we'll talk about how these things interact. So let's start from the beginning. And define a random variable. And a random variable, the definition I'm going to put on the board practically sounds circular. It's a variable whose outcome, I like this. I hope it's not uncomfortable for you. It's a variable whose outcome is the result of a random, I'll say, event, but in probability, we have a fancy name for these events. We call them experiments. So, you roll a die. So a 6-sided die, it can have numerical outcomes 1 to 6. And you record the value that you get. And there are things you could do. You could also record whether it's even or odd, for example, but we're going to look at experiments that have numerical outcomes. And when you see experiment, it makes it sound very clinical, very controlled. But you can think of almost anything as an experiment if you want to. Like, every day I walk to work. And I know that depending on my pace, it will take me 15, 20 minutes to walk to work. We can let the x be the time it takes me to walk to work. And of course, when I walk to work every day, I don't think I am going to perform an experiment. It's just something that happens. And random variables can be generally sort of dumped into 2 different categories. They can be what we call discrete and what we call continuous. And I'm going to give the book's definition of a discrete random variable, even though it's not quite correct. A discrete random variable is what we have when an experiment has finitely many outcomes, and you roll a die, die singular. You roll a die, it's 1, 2, 3, 4, 5, 6. Those are the outcomes. There are finitely many of them. And we'll say that a random variable is continuous if the possible outcomes are an interval. And so, let's say that when I walk to work, even if I sprint, I can't get there in more than 10 minutes. And even if I'm really slow, it won't take me more than 30 minutes. So something like this. Or maybe you want to include the possibility that I get hit by a car, and then you say, well, it can't be less than 10, but there's no upper bound. But either way, it's an interval. You'll notice that the way we've defined discrete and continuous are not quite opposites of each other. Because like if you had an experiment that could give you the natural numbers, well, that's infinite, but it's not an interval. As I say, these definitions aren't quite correct, but they're correct enough for us. And you have to deal with discrete and continuous variables differently. There's a fundamental difference between them. And that fundamental difference comes when you start asking questions like how likely is a specific outcome. You roll the die. We'll assume for simplicity that it's perfectly balanced. Every outcome is equally likely. So if there are 6 possible outcomes and they're all equally likely, they must all have a probability of 1 in 6. So this is simple. We just make a table. I mean, I say it's simple. If there are 1,000 possible outcomes, then creating a table with 1,000 entries will be extremely cumbersome. Maybe let's get this so it's not loading directly on Gabriella. Yeah, so because there are finitely many outcomes, because this is discrete, we can just name them all and we can name the probabilities. Now, this doesn't work for continuous random variables. Let's look at the time it takes me to walk to work. And let's say we're stuck in this interval. We always get there between 15 and 30 minutes. I might have said 10 on the last frame. Yeah, 10 to 30 minutes. Even though it's probably not realistic, let's try to let's try to grasp the idea that all of these outcomes are equally likely. I'm just as likely to take, 15 minutes as I am to take 20 minutes. Well, what we quickly discover is that that's not a useful way of approaching this problem. What we actually see is that the probability of any outcome has to be 0. And I think for most students, that's a very unintuitive idea. But I mean, first of all, let's see where it comes from. Suppose I'm trying to get at the idea that the probability of all of these outcomes is equally likely. Let's say the probability that it takes 15 minutes is, I don't know, let's say that it's 0.1. Well, if all of these probabilities are equally likely, then the probability that it takes 11 minutes is also 0.1. And the probability that it takes 11.2 minutes is also 0.1. And there are an infinite number of outcomes, and they all have a probability of 0.1, and that doesn't make any sense because the probability has to add up to 1. The probability that I get a time is 1. It doesn't make sense for it to be bigger than that. So if we just start grabbing numbers in this interval and adding up the probabilities, well, it quickly becomes greater than 1, and that doesn't make any sense. And, of course, this 0.1 is kind of a red herring. Even if I made this much smaller, well, select a million points in this interval. Those probabilities will add up to be greater than 1. So no matter how small I make this, if it's a finite number, we're going to run into this problem where the probabilities are more than 1. And the only way to avoid it is this. And as I say, I think this is unintuitive for a lot of students. I mean, the first unintuitive thing you might say, well, okay, but now when we add up the probabilities, they're all 0. And I mean, the sort of solution to that is, well, you can't add up all of these probabilities. There are an infinite number of them. There are, if you've taken discrete mathematics, there are an uncountably infinite number of them. We don't have addition, so we can't add them up and we can't get 0, and that's therefore not a problem. But there's also the weird intuition, right? That I walked to work this morning and I did arrive, and it did take me some amount of time to arrive. And our intuition is that if something has a probability of 0, it doesn't happen. But I did arrive, and it did take me however long it took. So, I mean, to try to sort of get around this, we have to remember that, we see these numbers like 10 and 30 and 15. But we're in the space of real numbers. So when I say 15, I don't mean about 15. I mean 15 followed by an infinite number of zeros. So I can get to work and it can take me around 15 minutes. But what's the probability that it takes me exactly 15 minutes? Not just the second, not just, the millisecond, but up to a billionth of a billionth of a billionth of a billionth of a second, up to the 10 billionth decimal place. It takes me exactly 15 minutes. Well, that's not going to happen. I mean, we might as well call it 0. And, yes, I walked to work today and it took me however long it took me. And we have this slight oddity that this happened, even though its probability is 0, but it will never happen again. If I am cursed to walk to work every day until the sun goes out, I'll never get this again. I mean, in fact, we can go further than that. If we look at every experiment that anyone will ever run for the rest of time, none of them will have this outcome exactly. So, saying that this probability is 0, what else could it be? I mean, but this does sort of leave us then with the problem, as it were, that okay, well, you can't just identify individual probabilities, they're all 0. How do we talk about probabilities? And also, how do we talk about probabilities being more or less likely? Like, let's say it usually takes me about 15 minutes. So if you ask me how long it takes me to walk to work, well, numbers near 15 should somehow be more likely than numbers near 30, but they can't be because all of the probabilities are 0. No event can be more likely than another. And calculus is the tool that we use to approach this issue. So to motivate it a little, let's go back to the 6-sided die. And let's look at a number line. Here's 1, 2, 3, 4, 5, 6. And here's 1, 6. The probability, if you draw them, this is how you would draw them. And you'd say, well, the probability of getting 1 is 1/6, and the probability of getting 2 is 1/6, and so on. And we observe that these probabilities are the areas of rectangles, because these have widths of 1, the area is just the height. It's 1/6. And if we had a weighted die, maybe we have a die that never rolls a 3. And to compensate, it's more likely to roll a 6. 1, 2, 3, 4, 5. Then you draw in those new rectangles, and the probabilities are still the areas of the rectangle. And whatever you do to these probabilities, that's not going to change. The probability is going to be the area of the rectangles. And you know, if I replace this with a 12-sided die, where we now have numbers from 1 to 12, again, it's not changing anything. The probabilities are the areas of the rectangle. So we have this idea that the probability can be thought of as an area under a curve, and then we say, oh, well, we have a tool for talking about that, integral calculus. Lets us talk about areas under curves. So let's say we have an interval from A to B. And the way I have this written, it looks like a finite interval, but it doesn't have to be. A could be negative infinity and or B could be positive infinity. Let's define a probability density function. So a probability density function is a function on this interval that has some properties. It's never negative. This represents probability, and probabilities cannot be negative. If we say it's not, if we have a badly discontinuous probability density function, we could wind up with some extremely weird results. So we just banish this, and you can relax that condition. You can sometimes be discontinuous if the discontinuity isn't too bad, but for our purposes, we'll just say this. And then the important one, well, I don't know why I said that. They're all important. That the integral from A to B equals 1. And again, these are representing probabilities, and the probability that something is happening is 1. So even before we go into any depth here, that's where that's coming from. And when we have, this is only for continuous distributions, I should say. Well, if it's not a continuous distribution, then the second statement stops making any sense. So instead of talking about the probability of a specific event, you know, the probability of a specific number being selected, we've used A and B. I don't want to use them again in this way. Let's see. E, of course, has a special meaning, but here I'm just using it as the number after the letter after D. the probability that your random variable is between D and E is defined as an integral. So going back to this example, let's say that it usually takes me around 15 minutes to get to work. We can't talk about the probability being 15. That's 0. There's no probability that it takes me exactly 15 minutes. But we could talk about the probability that it takes me between 13 and 17 minutes and say that that's close to 1, say 0.95. And here we have then the idea of this, again, we can't say, well, the probability of being 15, but we can talk about the probability of being around 15. So probability distributions are, well, some of them are nice. You know, if you have an interval from A to B, let's see, what am I trying to do here? Give me a second while I try to work things out in my head, even though I said this was nice. Yeah, then we can have a constant probability function, 1 divided by B minus A. And this is clearly always positive. This is clearly continuous, it's constant. If I've done this correctly, bless you, yeah. Because that 1 over B minus A is a constant, it can just pull right out of this integral. The antiderivative of 1 is x. We stick in B and we stick in A. One divided by B minus A times B minus A is 1. Exactly what we need for this to be a probability density function. Or, well, 1/3 of the things we need, but we talked about the other 2. This probability density function is called uniform. And your intuition here is that any, or let me say, all the outcomes are equally likely. It's hard to talk about in English because, again, all the outcomes are always equally likely. All the outcomes always have a probability of 0. But this is saying, you know, Unlike the walking example, where I was more likely to be near one number than another, I was more likely to be near 15 than I was to be near 30. There's nothing like this here. I'm just as likely to be near the beginning as I am to be near to the end as I am to be near the center. Other probability functions are considerably messier. Well, not always, but some of the really important ones will not fill you with joy when you see them. And, probably one of the most famous probability density functions. I'm going to use specific numbers here so that I can go to Desmos and we can take a look at it. But for example, 1 divided this by the square root of 2 pi times the exponential of negative 0.5 times x minus 3 over 2 squared. This we would cannot take this by hand, so you're going to have to sort of take my word on it. I mean, if you think about what you would do, well, you've got an exponential and then you've got a function inside the exponential. And the only thing we could possibly try that we know is U substitution, but U substitution is not going to work. Because if we try U substitution, we get du being some whatever, negative x minus 3 over 2. The derivative of the inside function is 1. So I haven't forgotten the chain rule. And then we look and, well, we don't have an x minus 3 and that's that. And yet probability distributions that look like this are really important. You've probably heard the phrase the bell curve at some point in your life. Maybe you've heard the phrase normal distribution. So 1 divided by the square root of 2 pi times e raised to negative 0.5 x minus 3 divided by 2 squared. So this is what it looks like, called the bell curve. On the theory that it looks like a bell, and we could, change these numbers, and this number up here is controlling sort of where the bump occurs. So if this example I've given, where I'm walking to work and I want it to take me about 15 minutes. This is the probability distribution I would use. You see there's a lot of probability around 15. The area below the curve is going to be pretty big here. Whereas if we go back to under 10 minutes, the area below the curve is very small. Or if we go the other way to more than 20 minutes, the area below the curve is very small. There was at one point, I'll call it a fad fad in probability. The idea that data should follow this curve, and that if it doesn't follow the curve, it's somehow a problem that needs to be fixed. I mean, that's the theory behind curving grades. You don't normally hear the phrase used that way now. Now, when you talk about a curve, it's usually just some kind of flat bump to everyone's grade. But the theory behind it is, well, we want a lot of the class to be, let's make this 75 so that this is over here. The theory behind it is, well, we want a lot of the class to be in the C range, and then we want only a few people to be failing and getting Fs, and we want only a few people to be doing really well. So, properly speaking, grading curves or curving grades is a kind of, I've always thought, a kind of weird and hostile thing to do, because it's based on the idea that the entire class can't do well, that wherever the majority of the class ends up, that ought to be a C. I've called it a fad. I mean, this is an important probability distribution, but now there's a better understanding that this is not some kind of divine revelation. I mean, we don't have to make data fit this. It has, I'm afraid it has a pretty grim history in some ways. You know, if you look at the idea of IQ, the idea of intelligence quotient, and trying to make IQ fit the bell curve, and there was a very strong racial component going on there. White researchers trying to make Black subjects fall in this side of it. Was not a good thing, but we're hopefully moving past that. So, what this leaves us with, and this seems like a pretty good place to stop. How do we summarize data? Like, if we look at this probability distribution, the uniform probability distribution, and then if we look at this, we look at a bell curve. Here, most of our data, most of our results fall inside this interval. Here, there's nothing like that. Data is just as likely to be over on the left as it is to be over on the right. And I mean, we can look at curves and say that, but we'd like to be able to measure, you know, numerically, how spread out is the data. We'd like to be able to look at this and say, well, this value here is kind of the average. So taking, you know, well, taking the average, a concept you are familiar with, and bringing it into the realm of probability and into the realm of calculus, since we're using the integral to study probability, is something that we will do tomorrow. I will see you all then, bright and early. On the test, you can use a note card. The sample test said you couldn't, but you can. I'll post the Canvas announcement as well.